So some solved problems for chapter 3. This one's kind of a conceptual one. Question 316 says, what should the speed of a stone that's been thrown upward at some angle look like as a function of time? So let's cut back to this figure right here, 317. If we throw a projectile up, what we can kind of do is say, okay, I want to look at the x direction and the y direction separately. Velocity is a vector. I can break it up. So I can kind of write it like this. And what's going to happen is there's no acceleration in the x direction, so the x speed is never going to change. That vector is always going to be the same length. In the y direction, there's acceleration. It's in the downwards direction, and so that's going to be in the opposite direction as the velocity was initially. And so this velocity is going to get smaller and smaller and smaller. Right there, the y velocity is going to be equal to 0, and then it's going to start to be in the downward direction. So you can kind of see that the speed is going to be the vector sum of the x and y components, and so I would expect the speed to start off fairly large and then get smaller, probably the smallest right about here at the top, and then the speed's going to start to go up again. Note, however, that the speed will not be 0 at the highest point because we have the x component right here. So taking a look at this guy right here most closely matches what we'd expect the velocity to look like. And problem number 10, here we have a case of constant acceleration but motion in two directions, and we have the swimmer that's going to kind of just barely make it into the ocean. One thing to keep in mind for any of these problems, that x and y are going to share the time variable. Very typically for any problem that you see in chapter 3, we're going to use y to solve for time and then stuff that into the x direction. Now, in the y direction, we have acceleration, and it's in the downwards direction, and we know that it's 9.8 meters per second squared. So the way that we kind of attack this problem is let's figure out how long it takes her to fall down this 9 meters. In this case right here, we're going to say, y naught. It's going to be that position right there. Again, very typically, we'll just say that's going to be equal to 0. Final position is going to be 9 meters. But let's take a look at the direction here. Very typically, we're going to say that's equal to the plus y direction. That's going to be the negative y direction, so it's actually going to be down by 9 meters. I'm going to say the acceleration is going to be 9.8 meters per second squared, but again, it's in the downwards direction, so we need to indicate that it's negative. And kind of what we want to figure out is we want to figure out what is the time going to be equal to. So let's take a look at our equations for a motion for constant acceleration. Pretty much anywhere you see an x, just kind of picture a y in there. We know that we don't want to use this guy right here. This one right here, well, we know the initial velocity, but we don't know the final velocity. And this one, again, same problem, it's got that velocity, so we pretty much have to use this equation right here. And kind of what I've done is I've gone ahead and I've written this expression right here, and anywhere that I've seen an x, I just replaced it with a y. And so let's go ahead and say, well, that guy is equal to 0. And in this case right here, we also know that v naught y is equal to 0. So we can kind of set that guy equal to 0. And we're looking for the time. So we're going to say, okay, 2 times y divided by the acceleration, square root is equal to the time. All I've done is I multiplied both sides by 2, divided by both sides by a, and took the square root. So square root of 2 times negative 9 divided by negative 9.8. Go ahead and you type that into your calculator, and we're going to end up with 1.36 seconds. And again, x and y share the time. Now what we want to do is we want to say, okay, well, we know position is going to be equal to velocity multiplied by time, and we know that she's going to travel 1.75 meters, so we know x is equal to 1.75, and now we know what the time is, and we're looking for this minimum velocity, so velocity is simply going to be distance divided by time, so 1.75 divided by 1.36, and it's going to work out to be 1.29 meters per second. And problem number 12, a projectile problem. We're given some initial y velocity, it's equal to 12 meters per second. We're given the initial x velocity that's equal to 20 meters per second. And if you weren't given the components, suppose you were given the magnitude and the angle, simply use trigonometry to break them apart. What we need to do is we need to treat the x and the y directions separately. Why? Well, because in the y direction we have acceleration, in the x direction there is no acceleration. So what we could kind of say is, well, what would the x velocity look like at any given point? Well, it would be the same. There's no acceleration, so the velocity in the x direction is always going to be equal to the initial y velocity. Well, what's going to happen to the y direction? Well, we know that there's acceleration. It's the downwards direction, and so it's going to be 9.8 meters per second squared. Down, very typically, we call that negative. Acceleration is in the opposite direction of the velocity, so it's going to slow down, get smaller, smaller, smaller. Here at the very tippy top, the y velocity is going to be equal to 0. It still has some x velocity, but that's okay. And the y velocity is going to start to increase, but now in the negative direction. So in part A, what we're looking for is we're looking for how much time is required to the highest point. Well, what do we know? Well, we know the initial velocity, we know the acceleration, and we know at the highest point that the y velocity is equal to 0. So let's take a look at this equation right here. Velocity in the y is equal to initial velocity in the y plus the acceleration in the y multiplied by time. In this case, we're looking for time. That guy is equal to 0, so we simply rearrange this guy, and we would say that the acceleration is going to be negative initial y velocity divided, the time is going to be equal to the negative y velocity divided by the acceleration. So negative 12 divided by negative 9.8, and we're going to get an answer of 1.22 seconds to the top. In part B, we're looking for, okay, well, how high does it go? In that case, take a look at this and just replace all the x's by y's. How high it goes depends on its initial position plus initial velocity, y velocity multiplied by time, plus 1/2 the acceleration in the y direction multiplied by time squared. We'll say it starts off at the ground, and the ground is equal to 0. So really it's a matter of just kind of plugging this in. So 12 multiplied by 1.22 plus 1/2 negative 9.8, and then the time squared, 1.22 squared. And we're going to work out an answer of about 7.4 meters. For part C, how long does it take, or how much time to return to the original level? Well, if it took 1.22 seconds to do the first half of this trajectory, it's going to simply take 1.22 seconds to come back down, so it's going to be a total of 2.44 seconds. You can also, so that's kind of doing it logically. You could also use these equations right here to do it mathematically if you wished. And for part D, we're asked how long did the football travel in that time. Remember that there's no acceleration, so the distance is going to be equal to rate times time, and this is all going to be in the x direction. So we can say, okay, it's going to simply be 20 meters per second multiplied by 2.44 seconds, and that's going to give me a distance of about 49 meters. And lastly, for part D, I've erased the work and I've drawn some graphs for x position versus time, y position versus time, velocity in the x versus time, and velocity in the y versus time. And heck, let's just do the x velocity first. We know that the x velocity is going to be a constant as a function of time. X position, simply going to keep on moving away from the rookie quarterback, and it's not going to do anything funky. The y position, well, we know that it's going to start off at the ground, go up to some high point, and then come back down to the ground. Now, the y velocity, it's going to be upwards, it's going to be positive, and it's going to get smaller and smaller and smaller and smaller. So, kind of do that, and at some point, it's going to be equal to 0, and then it's going to get larger and larger and larger, now in the negative direction, so it's going to look kind of something like that.